Hey guys, in today's video we're going to be going over binary, boolean functions, and microcircuitry, or rather boolean logic in a theoretical capacity that could be then used to create microcircuitry. So I know this probably seems a little bit out of character. I mostly do videos on chemistry and pharmacology, but when I was a teenager, I was really fixated on this topic, and so I figured that I'd kind of go back to my roots a little bit and hopefully explain in a somewhat comprehensible manner the basic concepts and ideas of these subjects. So what exactly is what is binary, right? You hear about it a lot in relation to computers and digital electronics in general. Rely on binary as the primitive form of processing data. We commonly use base 10 or decimal in our lives, and that would be the numbers 0 through 9, and then we have carryover, so it'd be 0 through 9, and then 1 0, 1 1, 1 2, and then you carry over again once you hit 19, and then you go 2 0. So it's like every 10 numbers you have a carryover, or I don't know the proper term. So base 2 is the same concept, except instead of every 10 numbers, it resets or it carries over every 2. Binary meaning 2. So you have 0 and 1, and those are the only relevant numerals in binary. Other examples of numerical systems include hexadecimal, in which 16 is the carryover point, and less common ones. But yeah, that's what binary is. But we're going to go more into detail about why it's so useful, especially in computing and in logical functions or boolean functions. And yeah, I'll get right into it. All right, so first of all, I guess I'd like to go over conversion of binary to decimal and conversion of decimal into binary. This is the way I learned how to do it. I'm sure there's probably more efficient ways, but in binary, being a model of base 2, the multiples of 2 are incredibly important. So you have, and I'm going to write these backwards. You have 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and so on. So if you want to convert a decimal number to binary, you have to use these values. And the way you do so is, so let's just say I want to convert the number 9 in decimal into a binary sequence or a binary number. You first take the highest number that's close to the number that you're trying to achieve. In this case, that would be 8. So you'd put a 1 there. And then you find the next one that adds to that 8 and results in the number you're looking for. So in this case, it would be 1. 8 plus 1 is 9. And then you fill in zeros for the other numbers in between. So 1001 would be 9 in binary. If you want a more complex example, let's say we're trying to get 69. So first obviously we would start with 64, because that's the highest closest number, and then 64 plus 4 would be 68, and 68 plus 1 would be 69. So 10000101. Now if we want to do the reverse of this and take a binary number, like I'm just going to write something random, 1, 1, 0, 1, 0, 1. You essentially just match it up here. So 1, 0, 1, 0, 1, 1. And then you add up where the ones are and ignore the zeros. So yeah, so that's conversion. Now I kind of want to get into boolean algebra and boolean functions. Boolean is kind of synonymous with binary. So the most simple example of this are logic gates. They're essentially just symbols that represent boolean functions. You have single input and you have multiple input ones, but for single input, for example, you could have a buffer, and this is and they're called logic gates because you have a signal passing through and passing through to the other side, and the gate provides parameters for that passage. In terms of a buffer, you're essentially letting in current and you're not letting it back the other way. And in real world application, this could be represented by like a diode or a transistor. So then we have an inverter. Now it looks the same as the buffer, right? But we have this little circle. And what that denotes in logic, in binary logic, is that the inverse of the input is outputted. So if the input of this buffer is 1, the output would be 1. If the input was 0, the output would be 0. And 1 and 0 in an electrical sense means, either no current, or otherwise low current or high current. So this being an inverter, input of 1 would equal a output of 0, and vice versa. These are just the single input gates. But then we have multiple input gates. So this is a OR gate. Now it has 2 inputs and 1 output. For this gate to let the current pass, at least one of these inputs has to be a 1. So, 1 and 0 would result in a 1 outputted, and 0 and 0 would equal a 0, and 1 and 1 would equal a 1. And then we have the inverse of the the inverse of the OR gate, which is the NOR gate, which is the opposite. So if any of the inputs are 1, it'll result in a 0. So for example, if it was 1 and 0, this would equal 0. Now next we have AND gates, represented by the D shape. And I have to say that these 2 input gates can also accept more than 2 inputs. They can accept 3 or more, and the conditions are still the same in terms of how the function applies. So with an AND gate, you have to have both inputs as 1s for the output to be a 1. So if you had 0, 0, it would equal 0. If you had 1, 0, it would equal 0. If you had 1, 1, it equals 1. And like I said, if you have any zeros in there, it's going to result in an output of 0. You can think of these in kind of like a more traditional mathematical sense, where an OR gate, the inputs are more additive. So if you have a current, if you have that current going into an OR gate, and you have no current going into the other input, it's still going to transmit the signal because 1 plus 0 is still 1. With an AND gate, you can think of it more multiplicatively. like if anything times 0 is 0, right? So you have to have no zeros in the inputs to have a 1 as an output. 1, 1, 1 times 1 equals 1. Now the reason, with an OR gate, 1 and 1 doesn't equal 2 is because we're operating under binary here. So, a current plus a current still equals a current in terms of like it's binary. It's either there or it isn't. Then we have the NAND gate. Sorry, I just realized I drew this wrong. This is the fuck. So this is I drew the NOR gate wrong. It doesn't have that little. It doesn't have that other loop coming off. That's a different gate. Sorry about that. So, so now we have the NAND gate, which is the inverse of an AND gate, in which 0 and 0 would output a 1. Next we have XOR and XNOR. Now XOR is what I accidentally, or XNOR is what I accidentally drew originally here, but XOR is a bit different. In that the inputs have to be opposite for the output to be a 1. So if you have 1, 0, it'll output 1. I'm going to show you the truth tables that represent these, and they're more easier to interpret. But then we have an XNOR gate, which is what I accidentally drew for the NOR gate. And this is the opposite of the XOR gate, as the name implies. If you have opposite inputs, then the output will be 0. So this activates if the inputs are the same, if it's 0, 0, or if it's 1, 1. So these are the common logical gates, and I'm going to show you how you can quantify them with truth tables. So a truth table essentially just shows inputs and outputs of these gates. So I'm going to start with just the single input ones. So we have the buffer, and if this is in, and that's out, if we had 0 in, we'll have 0 out. If we have 1 in, we'll have 1 out. Now, with the inverter, same principle but opposite. I'm just going to write I and O as the in and out. If we have 0 input, we'll have 1 output. If we have 1 input, we'll have 0 output. Now with the two input gates, like for example with OR, we have to provide a secondary input. So I'm going to label input 1 as A, and input 2 as B, and then the output as C. So if A equals 1, or sorry, we'll start with zeros. So if A equals 0, B equals 0, C is going to equal 0. If A equals 1, B equals 0, C is going to equal 1. And then the same thing if A and B are reversed. And then if 1 and 1, C will equal 1. And then NOR would be the opposite. Oh, sorry, on this OR truth table, I accidentally wrote 0 there, but I meant to write 1. So if there's any 1 in the equation in an OR gate, it will result in the output as being 1. And with the NOR gate, it's the opposite, and if 1 is in any input, the output would be 0. So you can see kind of the pattern here. So then we have the AND gate. Now 0 and 0, or 0 times 0 equals 0. 1 times 0 will equal 0. 0 times 1 will equal 0, and 1 times 1 will equal 1. So you see in this condition, it requires both inputs, A and B, to be 1 to provide a signal as the output. And for the NAND gate, so the polar opposite of the AND gate. So now finally we can move on to XOR and XNOR. So with XOR, which also, it stands for exclusive OR. So you can see it's exclusive in the sense that it requires the inputs to be of opposite binary value. And then XNOR, and as I'm sure you probably noticed by now, anything with the N prefix denotes the inverse of the respective gate. So with XNOR, it is obviously going to be the opposite. 0, 0 would be 1 output. 1, 0 would be 0 output. 0, 1 would be 0 output, and 1, 1 would be 1 output. So these are the building blocks of microcircuitry. So now that we've established what binary is, and we've established the logical gates and their respective boolean function, I want to talk about how this practically applies to microcircuitry. But before I do so, I kind of need to explain more about the laws and order of operations of Boolean algebra. So just like the decimal system, Boolean algebra has laws and orders of operations, and I'm going to start off with the laws. Fuck, I probably should have mentioned this sooner, but the V represents OR, and the inverted V represents AND. And then of course the lines over a variable represent negation. So next I'm going to go over the order of operations. This is important when you're working with an equation that has multiple operations within it. Negation takes the highest priority. While multiplicative operations, like AND operations, take medium priority, and additive operations take low priority. If you had the expression A or B and C, where would you start with this? You can rewrite this as A or parentheses B and C, where you would first calculate this value and then compare it with A. So next, let's say we have A and B, or C and D. This would be equivalent to A and B, or C and D. Now, what if we had multiple AND operators? What if we had A and B and C or D? This would be equivalent to double parentheses A and B and C or D. So in terms of negation, let's say we have not A and B, or C. And this one really just encompasses all of these orders. You would interpret this as not A, and whatever that value is, and B, whatever that value is, or C. So that covers it. That's important to understand before getting into drawing, actual circuits and understanding the Boolean expressions that they can be represented by. So I'm going to do that now. I'm going to draw a circuit and write the corresponding Boolean expression. The circuit is meaningless. It doesn't have any specific function. This is just illustrative. So we're going to have inputs here. We're going to have A, B, C, and D. These are variables that can be replaced with ones and zeros. I'm just going to randomly add some logic gates here. I'm going to do a total of 5, I guess. So and I'll say that the resultant output will be E, represented by E. So we drew a circuit. How do we test the circuit on paper? How do we quantify this with an equation? Well, first of all, I'm going to label the gates as G1, G2, G3, and G4. And they're tiered in a sense. So we can expand on the function of each gate. So for example, G1 would equal A and C. And G2 would equal B or C. And then G3 is a product of G1, X, or G2. So G3 would equal A and C. XOR is symbolized by a circle with a plus sign through it. B or C. And then G4 is equal to G3 or D. So put some double parentheses, A and C, XOR B or C, or D. So now we have an actual equation that we can plug this shit into. So if we give values to these variables, A, B, C, and D, we can plug it in and see what E will equal. And E will equal the sum of G4. So let's just assign some arbitrary values. So A, well, let's frame this as a conditional. So if A equals 1, B equals 1, C equals 0, D equals 0, then E will equal what we were trying to solve. So these are just random values that I chose. They could be whatever you want, as long as they're zeros and ones. So let's break this down. And in doing so, we're going to use the order of operations. So in the initial parentheses here, let's solve for G1 and G2. G1 would be A and C. If A is 1 and C is 0, then 1 and 0 is 0. So then let's solve for G2, B or C. Now B is 1, C is 0, so 1 or 0 is 1. So now let's say XOR. So what is G1 XOR G2, or 0 XOR 1? That's going to be 1. And then we finally have OR D. So 1 or D is 0 is 1. So using these inputs, E would equal 1. So yep, that's how you do it. That's how you take a drawn circuit and then write an equation for it, this G4 being the final equation. So how would you do the reverse? How would you draw a circuit based on a provided equation? So I'm just going to write a random equation. X equals A XOR B and A or C XOR C XNOR D. All right, so we have our equation here. So how do we draw this into an actual circuit? Let's start off with X. And let's look at this double parentheses section here. This is going to be a combination of two gates. You have A XOR B and A or C, but these are compared using AND. So this AND is going to be here, and then the sum of this AND expression will be compared by an XOR with this gate right here. So we know that the XOR gate is going to give us our final answer of X. So we have this kind of standalone XNOR. So we're going to say, so we're going to draw the XNOR gate, and this XNOR gate feeds into the XOR gate, which also takes the input from this AND gate. And this AND gate takes the input of two other gates. We have an XOR gate and a OR gate. So now that we have the gate set up, we just need to write the inputs. Since this first function is A XOR B, we can say A, B, C, D, and we could do A XOR B, and then we have and A or C. So A or C. Now these lines just crossing each other it means that they're not connected. If they were connected, they would have like a dot like drawn on them. This intersection right here, I could draw a dot here to represent that that is connected. And then we have C XOR D, where simply C and D feed into this XOR here. And then of course we can label these gates G1, G2, G3, G4, G5. And then we can solve for X if we set up a conditional here and give these variables some values. So if A equals 1, B equals 0, C equals 1, and D equals 0, just arbitrary values here, then X equals the sum of this equation. Starting off with G2, the A XOR B. Since A is 1, B is 0, A XOR B will be 1. Then we have A or C. Now A is 1, C is 1, so 1 or 1 is 1. And still working within these parentheses, we have G3 here, where we compare them with the AND. So 1 and 1. Now 1 and 1 equals 1. 1 times 1 equals 1. So then we have this secondary gate here with the C and D. C XNOR D would be 1 XNOR 0. And being the inverse of an XOR gate, that would mean that the output would be 0. You can think of it like this. Since C is 1 and D is 0, 1 XOR 0 would be 1, but then you have this negation that then converts it to 0. And then we have this final operation here, or function, where 1 XOR 0. So 1 XOR 0 equals 1. And so in this case, these variables are these values, then X would equal 1. So there you go. Now, just for fun, I guess, let's just do one more where we draw a circuit and we create the expression that represents it. Let's give it 5 inputs. Like with the first one, we start by labeling each gate. G1, G2, G3, etc. So you can see we have seven gates here, 5 inputs, 7 gates, and 1 output. So let's start with defining G1. Now G1 will equal A and B and D. So A and B and D. G2 is B XNOR C. And then G3 would be C or E. So G4 would be D and G3. So G3 being C or E, put those in parentheses, C or E. And D. So next G5. Actually, doesn't really make sense. I should have made this like a NOR gate, because an inverter is a single input gate. So we have two inputs there. So I'm going to change this to a NOR gate. So G5 would be G1 NOR G2. So we have G1 here. G2 is B XOR C. So then we would do you're going to be taking the inverse because it's a NOR gate. So G6. G6 is G2 XOR G4. So G2 oh, and I forgot to include that this is also negated. So G4 is C or E and D. And then we finally have G7, comparing these two, G5 and G6, with an OR operation. So that would be A and B and D, or B X NOR C, and then all of that is negated. And throw in some more parentheses here. Or B XOR C. Forgot to negate this here. B XOR C XOR C or E and D. Now we have our final equation, and we're going to give these variables some values. So I'll say if A equals 1, B equals 1, C equals 0, D equals 1, and E equals 0. Or 0. Then F equals question mark. So let's start breaking this down. Let's start off with G1 here. A and B and D. A is 1, B is 1, D is 1. So that will be 1. Because 1 times 1 times 1 is 1. So next we have G2, which is B XOR C. Now B is 1 and C is 0. So 1 XOR 0 would be 1, but negated would be 0. So we have 0 there. And then we have this OR operation. So 1 or 0 equals 1, but then with this negation would be 0. This is the solution to G5. So now we have to solve for G6. So we already know that G2 is 0. And now we have C or E. So C is 0, E is 0. So this will be 0. And D. D is 1. So 0 and 1. is 0. So now we have two zeros here, and we're comparing them with an XOR, and 0 XOR 0 is equal to 0. Finally, we have our OR gate, and so 0 or 0, and 0 or 0 is going to be 0. So if these conditions are met, then f will equal 0. So that's about it. I couldn't really think of anything else to mention. I guess I just thought that this was an interesting topic, and I hope that I covered it in an understandable way. It's a little unintuitive, I mean, like, we're taught base 10, and that's the model that we operate under in everyday life. So base 2 is a little bit, well, it's a lot different than that, and but the properties of base 2 make it very conducive to computing, whether it's electronic or, I mean, anything that can have two states of being can be used to make these boolean expressions and consequently these circuits. I mean, it doesn't have to be like electricity. I guess the takeaway from this is that binary and boolean algebra or boolean functions are incredibly important in the modern world. They form the basis of every electronic device that exists, and I think understanding it at like the microcircuitry level is interesting and fun, and there's a lot that you could do with it, both theoretically and practically. So yeah, that's it. Bye.